Welcome to my channel. Today I am going to show that pi is an irrational number. Okay, and for this proof we need to know only the first year calculus course. Okay, basically this proof has given by NIVEN in 1947. Okay, I am just following his proof. Okay, so I'm just following his proof in simplest way you can say that. So for this, at first, suppose that pi is rational number. If possible, let pi is assume that pi is rational number. So obviously, if pi is rational number, pi is equals to a by b, and as all we know that pi is positive. That's when we can say that a b positive integer. Okay. Now we are defining a function fx is equals to x to the power n a minus bx n factorial to the power n, where n can be any natural number, where n is a natural number. Okay, now clearly if we expand fx, so fx will be look like this: a0 x to the power n, a1 x to the power n plus 1, a2 x to the power n plus 2, and dot 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 an x to the power 2n. Okay, and the denominator is n factorial. So comparing this, we can say that a0 will be a to the power n, okay, and ai will be, sorry, let I plus 1, it will be good. A to the power n minus I, b to the power I, okay, and nci, and 0 less than is equals to I, get at less than n, okay. This is the ai plus 1. Clear? Just binomial theorem. You can see that just I used binomial theorem. Okay. Now, since it started from x to the power n. Now, if you try to think about the derivative of fx, okay, look at the first derivative, sir. Okay. So now if you think derivative of fx, suppose take I less than n, value of I less than n. If value of I less than n, and if you think of the derivative of f, okay, then you can say that since I less than n, so therefore after I derivative, in all the places x will be present. After I derivative, as I less than 1, after I derivative, in all places x will be present. If x will be present, if you put the value of x equals to 0, therefore all the terms will be vanish. So therefore you can say that if I 0 will be 0 when I less than n. Clear? And if you try to derivative I greater than equals to n, and try to think about if I is 0. Now think about that I equals to n. When I is equals to n, except this term, in all the places x will be present. Now if you put the value of x equals to 0, all the terms will be vanished except this term. And this term will be n factorial. Okay, and this term will be, suppose if you try to think fn as 0, except this term, all term will be vanished, and this term will be a0 n factorial. Okay, a0 n factorial, because you have derivative n times, so x to the power n, you will get n factorial upon n factorial. And if you think about if n plus 1 0, this term will be vanished, and except this term, in all the terms x will be present there. Now if you put the value of x equals to 0, then again all the terms will be vanished. So therefore if n plus 1 0 will be what will be a n plus 1 factorial. This time it will be n plus 1 factorial upon n factorial. So we can say that this term will be fi0 is equals to this fn n factorial, fn plus 1 n plus 1 factorial. So fi0 is equals to I factorial upon n factorial, okay, and a to the power I minus n, okay, because for n a0, for n a0, for n plus 1 a1, for n plus 2 a2, that's when you can say that ai minus n, okay. So ai minus n. Now since I greater than equals to 1, so therefore you can say that this term will be integer as I greater than equals to it. And this term also integer because it's a coefficient, it's a binomial coefficient where a b is integer. So a0, a1, a2, all the terms are integer. So therefore you can say that in any case, whereas I less than n and I greater than equals to n, in all the cases f(i0) is equals to 0. And if you think about the suppose f0 x equals to fx, if you think the f0 is equals to fx, then also you can say that f0 is also 0 as x to the power n. If you put the value of x equals to 0, this term will be vanished. So you can say that if I 0 is equals to 0 is integer for all I, okay. So therefore you can say that if I0 is equals to integer, 0 is an integer for all I, okay. Now if you think about the relation between f pi minus x and fx, okay, as pi is equals to a by b, so therefore you can say that pi is equals to a by b x, therefore a minus bx upon b, as fx equals to x to the power n, a minus bx to the power n upon n factorial. So therefore if you put the value of this part, so this part will be a minus bx to the power n upon b to the power n, and this part will be bn to the power n x to the power n and n factorial, okay, and b and n cancel, and finally you will get fx. So therefore you can say that if pi minus x equals to fx, so therefore you can say that if I x is equals to minus 1 to the power I f I pi minus x, okay, because if you fx one times, so f dash x equals to minus 1 into f dash pi minus x. Similarly again if you derivative two times, so f double dash x equals to minus minus plus f double dash pi minus x. So in the same way we can say that if I x equals to minus 1 to the power I f I pi minus x, that's mean now if you put the value of x equals to 0, it will be fi0 is equals to minus 1 to the power I fi pi. Now as fi0 is integer for all values of I, so therefore easily we can say that fi pi is also an integer for all values of I. So therefore we can say that fi pi is an integer for all values of I, okay, clear. So our proof of the first step is completed. Now we are going to the second step. In second step, we are defining a function. In second step, we are defining a function fx is equals to fx minus f2x f4x dot 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 minus 1 to the power n f2nx. Okay, we define this step function. Now clearly degree of fx is to the 2n. Degree of fx is 2n. So therefore you can say that any derivative higher than 2n, the f will vanish. That's when you can say that f m x equals to 0 when m greater than 2n. Okay. So therefore you can say that if you derivative f capital F two times, this term will be f2x, this term will be f4x, this term will be f6x, and this term will be 0, and before this term there is a term uh, plus minus 1 to the power n minus 1 f2n, and this term will be f2n f2n, wait, this term will be looked as f2n x. Okay, now if you comparing fx and f double dash x, you can say that except fx all the terms are present and sign is changed in every term. That's mean if you can say that minus fx, take common and fx, enter fx in this part, so it will look like this f2x, f4x, okay, plus dot 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 minus 1 to the power n f2nx, and the outside of the bracket there is fx, and finally you can say that fx plus fx, okay, and which shows that fx equals to f double dash x plus fx. Okay, so since now we have a relation fx equals to f double dash x plus fx, now there is a very important relation of fx and f dash x which is given by NIVEN. So I am going to prove this. So ddx of f dash x, f dash x sin x minus fx cos x. Now if you derivative this part, it will be f double dash x sin x plus f dash x cos x minus f dash x cos x and plus fx sin x. And if you take common sin x, so there will be f double dash x plus fx, it will be sin x. As fx equals to f double dash x plus fx, that's when you can say this fx sin x. Okay, since derivative of this part, since derivative of this part is fx sin x, that's when you can say that integration of this part is this. So therefore we can say that the integration of fx sin x will be f dash x sin x minus fx cos x. Okay, now let's take two limits 0 to pi, so therefore this limit will be 0 to pi. Okay, and finally you can say that f dash pi, this part will be 0, and this value f pi cos pi, value of cos pi minus 1, it will be f pi, and 0 again this part will be 0 and this part will be cos 0 1, so therefore f0. And as we know f pi and f0, now look at the uh, function fx equals to fx, f2x, f4x and f2x. Now if you put f pi, that's mean all f pi, f2 pi, f4 pi, and we know that f pi, fi pi, fi pi and fi0 all the integers, so therefore all f pi, f2 pi all integers, so therefore you can say f pi is an integer. Now if you put f0, x equals to 0, so therefore f0 is equals to f0, a small f0, f20, f40, since all the parts are integer, so therefore again f0 is integer, and hence you can say that this part is integer. And 0 to pi fx sin x to dx is integer. Okay, and so independent of n. Okay, and this part is integer for any values of n. Okay, because fx sin x dx is equals to integer for any values of n, as we have taken n is arbitrary. Okay, now we are going to show that this part will not be an integer for some fixed values of n. Okay, and there will be contradiction. Now we are going to show that this part will not be an integer for some fixed n, and there will be a contradiction because this fx sin x dx in integer for any values of n, and we are going to show that fx sin x dx will not be an integer. So let's prove this. Okay, so before starting this, we have to know the formula that we know that fx equals to, look at this, fx equals to a minus bx to the power n. Now if you take the limit 0 x pi, and as fx equals to x to the power n a minus bx to the power n upon n factorial, and a b are positive, that's when you can say that uh, fx greater than 0 and less than uh, the maximum value of x will be pi, so pi to the power n, and this part, maximum of this part will be a to the power n, as a is positive, and n factorial. Okay, and also you can say that sine x is also lies between 0 and 1. Okay, sine is also lies between 0 and 1. Okay, but if you here you taken 0 to pi, that's mean you can neglect 0. Okay, you can neglect 0, that's when you can say that since this part less than pi to the power n e to the power n factorial, so hence you can say that 0 to pi fx sin x dx is less than 0 to pi to the power n e to the power n upon n factorial dx, which is equals to pi to the power n plus 1 a to the power n upon n factorial. Okay, and then let this equals to pi un upon n factorial, where un is pi to the power n a to the power n. Okay, okay, we can say that it's pi to the power n plus 1, so we can say this pi into un upon n factorial. Now clearly un upon n factorial tends to 0 as n tends to infinity, as n tends to infinity. Okay, because un is fixed, un is constant. Okay, and easily we can show that this part is tends to 0. Okay, as this is a element of e to the power x. Okay, if you take e to the power e to the power un. Okay, say e to the power pi a, if you trying to find e to the power pi a, basically this part is a element of e to the power pi a, as e to the power pi a is convergence sequence, so therefore this part tends to 0, must be tends to 0 as n tends to infinity. Now as this part tends to 0, so therefore you can say that there exists a natural number m belongs to n such that un upon n factorial less than 1 upon 5, 1 upon 5 for all n greater than equals to m. Okay, un upon n factorial less than 1 upon 5 for all n greater than equals to m. And as un is equals to, pi n e to the power n, that's when you can say that after multiplication you can say that it will be pi to the power n plus 1. Okay, and uh, n factorial a to the power n less than 1, and this is the value of the integration. And also as fx and sin x both are positive in 0 to pi. Okay, both are positive in 0 to pi, so therefore it's also greater than 0. That's mean you can say that in the value of this integration, if you take I, value of this integration I, so therefore you can say that the value of this integration I is less than 1 and greater than 0. Okay, but we know there is no integer which is lying between 0 and 1. There is no integer which is lying between 0 to 1, and I is the value of this integration. Suppose this is I, so I is the value of this integration, and there is no integer which lies between 0 to 1. That's mean value of this is not an integer for all n greater than equals to m, which is a contradiction, because already we have shown that this part is 0 for any n, and now we see that this part is not integer for all n greater than equals to m, which is a contradiction. So therefore our assumption is wrong. What we have assumed? We assume that let pi is equals to a by b, where ab is positive integer, which is not possible. That's mean we cannot write pi as ratio of a by b where a b is positive integer. So therefore pi is not a rational number. Okay.